All right, so I don't have a video on phase diagrams, so I'm making a new one here. You're going to have to deal with the announcements for bus riders being dismissed, but I wanted to get up a video there so that you have it for review. All right, so phase diagrams, again, we talked a little bit about how you can get a solid piece of ice at temperatures even above the freezing point. Or you could get liquid water at temperatures even above the boiling point. And you do this by manipulating pressures. Increasing pressure would allow you to have liquid water at temperatures above the boiling point. This is what happens in the radiator of a car. The radiator system is under pressure, and that pressure extends the liquid phase of the water beyond 100 degrees Celsius. And that's basically what this slide here is all about. How about the inner core and the outer core of the Earth? The inner core is solid, even though it's extremely hot. The inner core's temperature is about the same as the outer core's temperature, but it's solid because of all the pressure on it. There's so much pressure, it literally squeezes the particles together enough to make it a solid, force them into fixed positions and make them vibrate. And again, these phase diagrams allow us to see what state we would have at pretty much any combination of temperature and pressure. So it's divided into three parts: solid, liquid, and gas. And as I mentioned, the solid part of the phase diagram is the part furthest to the left. That's where you're going to find all your solids. And this one says ice because this is water's phase diagram. But again, it could be any substance, basically solid in this white section. All the way over to the right and extending across the bottom is where you find the gas. And again, it says water vapor here, but this is any substance. This is where you're going to find the gas. And of course, between the two, you'll find the liquid phase. It says water here, but that is the liquid phase. So solid in the white part, liquid in the blue part, gas in the yellow part. The lines dividing each segment are where the state changes occur. So this line here is between the solid and liquid. So this line here represents melting and freezing. Melting if you're going from solid to liquid, freezing if you're going from liquid to solid. This tells you the freezing point of the substance at various temperatures and pressures. This line here divides the liquid and the gas. So this line here is where melting, vaporization, and condensation are happening. Vaporization if you're going from liquid to gas, condensation if you're going from gas to liquid. And then finally, you have this line down here. There's a couple of special state changes called deposition and sublimation. That's where the solid and gas are, you're moving back and forth between the two without going through a liquid phase. So if you're going from solid to gas, that's called sublimation. If you're going from gas to solid, it's called deposition. And again, this line will tell you what temperature and pressures you would need to have those two state changes happen. So again, this line is where you're freezing and melting. So this is where you would look to find your freezing point. This is water. So at 1 atmosphere of pressure, which is the pressure at sea level, the freezing point of water is 0 degrees Celsius. Now, freezing point and melting point are the same temperature. It just depends on if heat is being added or removed. This line here tells you the boiling point of the substance. Boiling, of course, if you're adding heat to it. Condensation would be happening if you're removing heat from it, but there's no real name for that temperature at which the gas turns to a liquid. And for water, there's things like dew points. Not really the same thing because it depends on humidity. So again, we look at water, 1 atmosphere of pressure. That's normal atmospheric pressure. 100 degrees Celsius is the boiling point. So as your pressure increases, you can see that your boiling point would also increase. This is what a pressure cooker does. It increases you from 1 atmosphere of pressure up to something higher. that would cause you to be further up the line and give you a higher boiling point. And of course, the boiling point can be lower than 100 if you drop the pressure. We talked about climbing to the top of a mountain. That would drop the pressure. You'd be somewhere here on the line now, and your boiling point would be lower than 100. Again, this is where deposition and sublimation take place. And again, you can find the combinations of pressure and temperature where that happens. There's two special points on the graph. We have this one here and the one up top. This is called the triple point down here at the bottom. This is where all three states are in dynamic equilibrium. So you have solid, liquid, and gas all at the same time. You have melting, freezing, boiling, vaporization, sublimation, and deposition all happening at the same time. So all the state changes in all the states in your container all at once. So you can imagine ice sitting in boiling water, but that ice cube doesn't get smaller. You'd have steam coming out of it just the same as you had condensation raining down into it. But again, the water level wouldn't change. Everything's happening at the same time, and everything is in equilibrium. That's the triple point. Again, all the states at the same time, all the state changes at the same time. Everything is in dynamic equilibrium. At the top, you have the critical point. This is where you create a supercritical fluid. At this point, you can no longer tell the difference between a liquid and a gas. It acts like both. It acts like a gas in that it diffuses through the tiny holes in solid matter, like the helium gets out of a helium balloon. And it acts like a liquid in that dissolves stuff, like salt would dissolve in it. So it acts both like a liquid and a gas. You can no longer tell the difference between the liquid and the gas. We call that a supercritical fluid. Every different substance has its own diagram.
Out of six.
So again, the places where the lines meet, how big the solid part is, how big the liquid part is, that all changes from one substance to the next. But you still have all the same parts.
Star 4, star 5, out of 6, star 4, star 5, and out of 6.
So over here you have a solid, just the same as on this one you have a solid, same as this one you have a solid. On the bottom and towards the right, that's where you find the gas.
Star 7, out of 2.
All the same, and again, liquid is in between.
Star 7, Flat Rock 2.
Well, there you go. Just in time for all the bus announcements to start. Hope that helps. Have a great day.